everyone, welcome back. In this particular video, we will be discussing the problem. Find the kth smallest element in a matrix. We are given a n cross n matrix, a square matrix, you can say, where each of the rows and the columns are sorted in increasing order. It means individually all the rows, individually all the columns will be in increasing order, will be in sorted order. What we need to do is we need to find the kth smallest element in this corresponding matrix. An important note which they have given is it is the kth smallest element in the sorted order, not the kth distinct element. It means if there are duplicate elements also, then also you have to just consider the kth smallest. Let's say if I'm saying there is a 1D array, just discard the matrix part now. The 1D array is containing 10, 20, 20, 30. In this case, I will say that the first smallest element will be 10, second smallest element will be 20, third smallest element will again be 20, because we don't have to consider distinct elements, we can consider duplicates. So second smallest as well as third smallest can both be considered 20, and then fourth smallest can be considered 30 in this particular 1D array. So I hope the note point is clear to everyone. Anyways, coming back, so what we are given is a square matrix where each row and each column is sorted. So the example which they have given in the sample input is a matrix having 3 rows, 3 columns, and the k value, the kth smallest element which we need to find out is the 8th smallest element in this question. So let's draw this matrix in the notes. First of all, we are given in the first row 1, 5, 9. There are 3 values. Then again 3 values 10, 11, 13. And in the next row again you are given 3 values which are 12, 13 and 15. 12, 13 and 15. And as you can see, the array or the matrix can contain duplicate elements also. What we need to do in this, we need to find the 8th smallest element in this corresponding matrix. The answer according to the output, the sample output is 13. And why is it so? If I will just write all these elements into a sorted order, into a one single array, a array of sorted elements, then what will the sorted order become? 1. Then of course next element will be 5. Then next element will be 9, then 10, then it will be 11, then it will be 12. Like you can just pick the smallest element each time. So this will come out to be the sorted elements. Obviously, it will have 9 elements, because if the matrix is 3 cross 3, the array corresponding to the matrix in sorted order will be 3 cross 3 only. That is 3 into 3, 9. Now, in this array, this is the first smallest element, second smallest element, third smallest, fourth smallest. We have to consider one based indexing. Fifth, sixth, seventh, and the 8th smallest element will come out to be 13, and that's why the answer they are showing is 13, because we have to consider duplicates also. So one very basic approach, one very brute force approach which must come to your mind is this approach, same approach only which we have just now done to understand the problem. What is that? How about ignoring the fact that matrix is given, matrix have individually sorted rows, individually sorted columns? Ignore all of those information, ignore the problem statement completely. Just do what? Just convert the matrix into a single sorted array, into a single sorted array. How you can do it? You can do it actually in very different number of ways into a single array. How you can do is basically first, you can just put all the elements row by row into an array. That is first 1, 5, 9, then 10, 11, 13, and then 12, 13, 15, and then just sort that array using inbuilt sorting functions. So what will be the time complexity of converting the matrix into a single sorted array? If I'm considering there are n rows, n columns, so obviously array will be of n square size, n into an n square. And to sort that array, it will take n square log n square. So converting the 1D array, actually 2D array into a 1D array will take this much time complexity. Log n square is log n only. So it will be n square log n. And then to find the kth smallest element, you just have to go to the 8th corresponding element, which is nothing but here it will come out to be 7th index. Why? Because in 1D arrays, the always indexing starts from 0. So we can just say now return the k minus 1th index. Return the arrays k minus 1th index. But since, as you can see, we are converting the matrix into a single array, first, of course, we are taking huge time complexity because we are going to sort that 1D array. And then, of course, we are also taking space because we are creating a 1D array of n square size. So this much will be the time complexity for the brute force, and space will also go out as order of n square because we are taking a new array of n square size. But There can be small optimizations in this brute force. The way you are creating a single array can be created in an optimized fashion, considering the fact that all the rows of this matrix are sorted. So you can actually apply a two-pointer kind of strategy, that is merge k sorted arrays. This is one sorted array, this is another sorted array, this is another sorted array. So you can just use individually each row as a individually sorted array and merge them by applying the logic of merge k sorted arrays. But I'm not going into that much detail, because even though it will reduce the time complexity from n square log n, but still it will be very much uh, not, you can say, optimized. It will be a better solution than brute force, but not the most optimized one. The point is, we have to do something in the matrix itself. We have to find the kth smallest element in an optimized fashion. If we are searching for it within the matrix, we are not creating an array, then only we will be saying that we are able to do it in optimized fashion. So given that we need to find the eighth smallest element, what we can say is we can apply a searching algorithm within the matrix. We are not doing sorting and then just returning the array element. We will be searching for the kth smallest element. And we are searching in a matrix, so matrix should be sorted. But the point is, matrix is sorted in each row, that is, each row is in increasing order. Matrix is sorted in each column, but it is not given that each row is sorted and then the next row will start from the next element. You can't say that all the elements will be sorted row by row. That is 1, 5, 9, then 10, 11, 13. Till now it is sorted. But now when you will go from 13 to 12, it is not sorted. It is now in decreasing order. So you can't say that each row will be more than the previous row. That is, the first element of the ith row will be more than the previous row's last element, because this is invalid in these two rows. Similarly for columns. So since the entire matrix, it's not sorted according to what we can actually do binary search on, that is according to a 1D array, we have to do a modification in the binary search. We have to do a modification in the searching logic. And that modification will be, we will not actually search for the target element, because we don't know what is the target. We don't know which element will come out to be the eighth smallest element. So we will apply the binary search on the answer itself. This is a concept which we have applied on various problems. Like there was a problem based on the speed. There was a problem based on different other concepts. Like there was a problem based on the square or the square root actually. So we have to apply the concept of binary search on answer. That is, whatever the answer will be, that we have to search using binary search. Now, what is answer? The kth smallest element. What is the range of that answer? That is answer, where is the range on which the answer can lie? I will say the kth smallest element, the eighth smallest element can be minimum one, that is a minimum element in the matrix. Because if let's say I am giving k as 1, what is the smallest element, the first smallest element? Of course, you will say the smallest element in the entire matrix. So range will be the array of 0, 0. That is the top left corner. Why? Because it is minimum in the row as well as minimum in the column. But what about the maximum element? If you will say that the range right side value, the highest value, what will be that? Of course, we can say that will be the highest value of the matrix, which is in this case 15. That is our rightmost corner element, array of n minus 1, comma n minus 1. So the answer can lie in the range of array of 0, 0 till array of n minus 1, n minus 1. Or you can in general say that the range will be whatever the constraints is given. So since constraint is array values will be from 0 to 10 to the power 9, so you can consider the left value as 0, you can consider the right value as 10 to the power 9. That will also work. Whatever you want to apply the logic, like in whatever way, you can do it. Anyways, let's for now just take, during the dry run, let's take the left value as 1 and right value as 15. So I'm just drawing an imaginary array. It is not present. It is just a number line from 1 till 15, from left till right. So let me just start the number line a little bit from the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we are doing the dry run for, let's say, k is equals to fifth element. Okay, so what we will be doing is, we will be applying binary search on this range, the answer range. So the minimum element will be array of 0, 0, that is the top left corner. the maximum element will be the rightmost element, that is array of n minus 1 comma n minus 1. This is the left range, this is the right range. We will search for the mid. Mid will come out to be left plus right by 2, 1 plus 15 by 2, which is 8. Now ask to the mid element. What do we need to ask to mid element? We will check whether mid can potentially be the answer or not. Now there are two scenarios whether mid element will be a potential answer or mid element will not be a potential answer. Since we need to find out the fifth smallest element, let me first write all the elements in the range from the first smallest till the eighth smallest, or actually ninth smallest, because there are total 9 elements in this array. The smallest is 1, then next is 5, next is 9, next is 10, 11, 12, 13, 13, 15. So what we need to report the answer is, we need to report the answer as the fifth smallest element, which is 11 in this case. We need to find the element 11. What we will say is whether the mid element is the fifth smallest element or not. That we will check by checking it whether it lies in the range from 0 till the element from 0 till actually the first smallest element till the fifth smallest element, and the other range will be from the fifth smallest till the ninth smallest. That is, one of the range will be from 0 till k minus 1, not including k, and other range will be from k till the last element. And if we are able to find out whether 8, the element, either it will be present in the matrix or not, that does not matter, because right now we are just saying it is either going to be the potential answer or it is not going to be the potential answer. We are not saying it is final answer. So 8, whether you lie in the range 0 to k minus 1, whether you are the element which is the smallest or the k minus 1th smallest in this range, or whether you lie in the range from k till the last element, till n square minus 1, n squareth smallest element, that is in this case ninth smallest element. If we are able to do this, then we will say whether it lies in this range, then yes, it can potentially become the answer, and we will try to go to the closer element. If let's say 8 comes out to be the seventh smallest element, let's say for now, we need to find the fifth smallest. So we will go to the fifth smallest by reducing the range, by reducing the right pointer. However, if we are, let's say, landing on an element which is in this range, let's say we are landing on the element 5. We are saying 5, since you are the second smallest element, what we will say is go to the right hand side by updating the left pointer. So this is how we will be able to deduce the divide and conquer strategy. Whether the element is in the range 5 till 9, then yes, it is the answer, and update the right pointer by making it mid minus 1. Whether the mid element is in the range 0 to k minus 1, so don't update the answer. It is not the potential answer. Potential answer will be the fifth smallest. But update the left pointer as left is equals to mid plus 1. Now the only thing remaining is how to check whether 8 lies in this range or in this range. So for that, we have to count that how many elements are smaller than 8 or how many elements are greater than or equal to 8. Then only we will be able to check whether 8 is the kth smallest element or not. Because if for these elements we will say how many elements are smaller than 10, you will say 3 elements are smaller than 10. How many elements are smaller than 9? 2 elements. Smaller than 5? 1 element. Smaller than 1? 0 element. So can I say for the first range, the elements smaller than the target, smaller than whatever we need to search for, the count of elements smaller than that value will be less than k for this particular first range. And for the second range, the elements smaller than that corresponding element, let's say for 11, how many elements are smaller than 11? You will say 4 elements are smaller than 11. Or you can say how many elements are greater than 11? You will say greater than or equal to 11. It will be all the remaining elements. So number of elements which are smaller than 11 or smaller than actually equal to 11, it will be 5. How many elements are smaller than or equal to 12? It will be 6. So if you are just saying count here will be less than k, but count here will be greater than equal to k. Here count will come out to be greater than equal to 5. Here the count will come out to be less than 5. That is up till maximum 4. So this is how we will be able to deduce whether an element is in the first range or not. And now the point remaining is how to check, how to find the count of elements smaller than a given element, smaller than or equal to a given element. So for that, we have to again go back to the matrix. So let me just copy this matrix on the next page. Let's just try to find how many elements are smaller than the current mid element, which is 8. Count of smaller elements. So I'm just writing count of smaller or equal to the count of elements which are smaller than or equal to 8. Initially, we will say, of course, that number of elements are 0. In order to find how many elements are smaller than equal to 8, what we can do is we can simply just apply a binary search on each row, because we know each row is sorted. That is one strategy. That is, apply the binary search on first row, find where the 8 will exist. All the elements smaller than that will contribute in the count. Similarly, in the second row, find where 8 will exist. Smaller elements, update the count. Find where 8 will exist. Smaller elements, update the count. But other way is using a variation of step case search. If you know about step case search, well and good. If not, then just for now, follow along the video, because this is not a very intuitive solution for now, because we have already applied binary search on answer, which itself is not very intuitive. And the second point is to find out the count of smaller elements. That also is not very much intuitive. The count of elements smaller than the current element, the current mid element. So we will say start from the top row, from each row, and within that top row, we have to go to each and every row, find elements in each every row. How many elements are smaller than 8 in first row, in second row, in third row. But start from the top right corner. That is, initially the row will be the 0th row. This is R0, R1, R2. Column will be the last column. That is n minus 1th column. Ask this element, is it more than mid or is it less than mid? You will say it is more than mid. Since it is more than mid, will it contribute in the count? No, it will not contribute. Since 9 is not going to contribute in the count of elements less than equal to 8, will 13 or will 15 contribute in the count? We will say no. Since this column is sorted, we will say all these elements will not contribute in the count. So discard this column. How we can discard this column? By doing column minus minus. The row was 0, column was 2. Now row will remain 0, but column will become 1. Now 5. We are saying 5 is less than equal to 8. It will contribute in the count. But not only 5, 1 will also contribute in the count. Why? Because 1 is also less than equal to 8. Since the row is sorted, all the elements in the left side will contribute in the count if the current element is contributing. That is, how many elements are contributing in the count? We will say column plus 1, 2 elements, 1 plus 1, 2 elements are contributing, 1 and 5. And since we have counted them, discard them. How to discard them? By going to the next row. This row is discarded, this column is discarded. So now what is the top right corner? This is the top right corner. So if we are discarding a column, column minus minus. If we are discarding a row, row plus plus. Now, 11, is it less than equal to 8? Is it less than equal to mid or more than mid? 11 is more than mid. Since 11 is more than mid, all these elements in the column below it will also be more than 8, because 11 is more than 8. All these elements are more than 11. So all these elements are more than 8. So they will never contribute. So discard this column by doing column minus minus. Here we were doing column minus minus, row plus plus. So go to the previous column. Ask to 10. 10, are you less than equal to 8 or more than 8? 10 is also more than 8. So discard the column. And as soon as you will discard the column, you will go to the previous column. Column will become minus 1. That is out of the matrix. So only 2 elements were less than equal to 8. How many elements were we required? We at least require 5 elements. We at least require k elements to be smaller than equal to mid, if that is going to be the potential answer. Now, since the count of elements smaller than equal to mid is only 2, it is less than the k value, it is not going to be the answer. 8 can never be the fifth smallest element. Since elements which are smaller than 8 are only 2, how can 8 be the fifth smallest? For 8 to be the fifth smallest, there should be at least 5 elements in the left hand side, including itself. So since 8 is not the answer, what we were doing in the range when the answer is not possible, increase the range by updating left pointer. That is, left will now become mid plus 1. So we will go to 8 plus 1 and now check the new mid. So we will say, what is the new mid now? Let me just remove all of these dry runs. The new mid will come out to be 9 plus 15 by 2, which is 24 by 2, which will come out to be 12. Ask the same question to 12. How many elements are less than equal to 12? And if it is in this range, that is, if the number of elements smaller than equal to 12 are less than 5 or more than equal to 5, on that basis, we will update our answer. Initially, what we can assume our answer is, we can assume our answer as any element. We can assume as 1, as 15, anything as you want. Let me just initialize it with the maximum value right now, which is 15. So initially answer was 15. Now I'm checking 12. Is it going to become the answer? So again, apply the same binary search. So for that, I've just copied the matrix again. This time mid is 12. How many elements? are less than equal to 12, initially the count will be 0. Again, start the step case search starting from the top right corner. Is 9 less than equal to 12? Yes, this time. So all these elements are also less than equal to 12. All these elements will contribute to the count. How much count will they contribute? We will say whatever the column value will be, all those elements, that is column plus 1 elements, 2 plus 1, 3 elements are there, which are contributing in the count. And now since all these elements are done, row plus plus, because we have counted them. 13, is it less than equal to 12? No. So since 13 is not less than equal to 12, all these elements are also not less than equal to 12. So discard them by doing column minus minus and don't update the count because they were not less than equal to 12, not less than equal to mid. Is 11 less than equal to mid? Yes. So all the row elements will of course also be. So what is the column? Is 1. So count will become 1 plus 1, 2, column plus 1 and row plus plus. Go to the next row. 13, again it will not contribute. Column minus minus. 12, yes, it will contribute. Equal element will also contribute. How much? Column plus 1, 0 plus 1 element only, 12 itself. And as soon as you do row plus plus, it will go outside the matrix. So how many elements are there which are contributing the count? We will say 6 elements are there. And now, since the number of elements are more than equal to 5, more than equal to k, we can say potential answer is 12. And 12 is not the final answer. It is a potential answer. It can become the fifth smallest element if there are no elements in the left side, which are the potential answers. But now we will reduce the range. Since we are saying it is a potential answer, not the final answer, try for a smaller value. That might become the answer. Right will become mid minus 1. Again, check for the mid value. So we will say mid this time will come out to be left plus right by 2, 9 plus 11 by 2. Mid will come out to be 10. This time, if you will check for 10, I'm not doing the try run again. How many elements will come out to be less than equal to 12? 10. 1, 2, 3, 4. Only 4 elements will be less than equal to 12. So it will come in this range. So since it is not going to become the answer, increase the range by making left is equals to mid plus 1. And now if you will check the new mid, that is count for the new mid, mid will come out to be left plus right by 2, which is you can say 11 plus 11 by 2. So 11 plus 11 by 2 will be 11 only. How many elements are less than equal to 11? 1, 2, 3, 4, 5. 5 elements are less than equal to 11. So it comes in the potential answer range. Since it comes in the potential answer range, update the answer. Yes, 11 can become the fifth smallest element. And now, since you will reduce the range, because whenever we are having the answer, the mid element in the potential answer range, we are reducing mid. As soon as you will do reduce mid, right will become less than left. And that is when the binary search will break. The entire array is being searched. What is the final answer? Final answer is 11. And as you can see, actually the answer is 11. The fifth smallest element is 11. So this is the optimized solution, which we are doing using binary search on answer. Every time we are saying that apply the binary search not on the matrix, not on the array, but on the answer itself, which will be from the range array of 0, 0. This is array of 0, 0 till array of n minus 1, n minus 1. Check the mid, whether it comes in the potential answer range or not. How to check? For that, count number of elements less than equal to that mid, whether it is less than k or greater than equal to k. If it is greater than equal to k, yes, it is in the potential answer range. If not, then don't update the answer. And keep on doing this, keep on reducing the search space till we are getting the answer value. So now since the approach is clear to everyone, what will be the overall time complexity we discussed right now just before writing the pseudocode, the instruction manual? Since we are applying a binary search on an array of answers, what will be the array of answers or what will be the range of answers? The minimum value till the maximum value. If I am saying value is v, applying binary search on a range v will be log of v times. But every time, in order to apply binary search, what we are doing, we are finding the count of elements. And for that, we are doing step case search. What is the time complexity for step case search? If you will see very carefully, every time either we are discarding the column or discarding the row, discarding column or discarding row, and so on. So since every time we are either doing row plus plus or column minus minus, we will in total do n times row plus plus, n times column minus minus. So it will come out to be n plus n, which is 2n, which is n only, where n is the number of rows, number of columns, linear. So each time in each binary search iteration, we are doing n time complexity step case search. So overall code's time complexity will be log of v times n If you are saying in general v is also comparable to n, so you can say it is n log n. So overall time complexity due to binary search on answer will come out to be n log n, which is of course less than n square log n. N square log n has 2 times n terms, that is n into log n. But now it is only n times log n. So now since we know the approach, let's just write the instruction manual. First of all, what we need to say that whatever the matrix is given to us, we will apply the binary search on it. So set 2 pointers, set the left pointer as the array's smallest value as the top left corner element of matrix. Also set the right pointer as the maximum value, the bottom right corner element of the matrix. Once we are able to get these 2 elements, we will start the binary search. Till when we should run the binary search? Till run a while loop till the point. We all should know that when should we break from the while loop. Till the point left is smaller than or equal to right, we have to apply binary search. What we will do is find out the mid pointer. So set the mid pointer as left plus right by 2. That is not a rocket science for now, because we all know binary search, we all know divide and conquer. But what we need to do for mid? Do we need to search it in the matrix? No, we need to find the count of elements. So find count using a function. Find count of smaller or equal elements than mid from a function. We will write the function. Now check whether this count is less than k or not, because we have to check whether the element lies in the potential answer range or not. If the count is less than k, it is not the answer. If it is more than equal to k, it can be the answer. It is not the final answer. So if this count is less than k value, the kth smallest element which we need to find out, it is not the answer. So don't update the answer, but at least do what? Increase the range by making left is equal to mid plus 1. Let's say we are standing on 5, we have to go to 11 by increasing the range. If we are standing on 13, we have to decrease the range. So on the range which is having count less than k, increase the range by making left as mid plus 1. However, in the other side, what we have to do? We have to do 2 things. First, of course, update the answer because it is the potential answer. So update answer as the current mid element. And also do what? Decrease the range by making right as mid minus 1. For that, of course, we have to make the answer variable. So set answer as the rightmost element, the maximum element. It might become the answer itself, or you can initialize it with anything. You can also initialize it with the left. So finally, what we will do is we will just return the answer, but the only point remaining is how we will find out the count. For that, we have to define a different function that will return me the count. Find count, let's say, find count smaller or equal. This is the function name I am giving. I am passing the matrix which we are given, whatever language you are using, you can just pass the same matrix. You will pass the mid element, that how many, what is the target which we need to check whether how many elements are less than that or not. So using stepped case search, what we are doing, we are basically initializing a row pointer, set a row pointer as the 0th row, start from the top row, and the column as the last row, as last column, which is n minus 1, if n are the total number of columns. So start from the top right corner to the step case search till the pointers are within the range. Until when will they be within the range? Since left is the row pointer is going row plus plus, row plus plus, row plus plus, it will be within the range if it is less than n. Since column is becoming column minus minus, column minus minus, column minus minus, it will be within the range if it is more than 0, or you can say more than equal to 0 actually. So run a while loop till when? We will say row is less than n, and as well as the column is greater than or equal to 0. Every time check for the current element. If current element at row comma column, we will say at row comma column, is it less than equal to mid or is it more than mid? If it is less than equal to mid, then yes, all the elements in the current row till the current column will become the answer. So update count, initially count will be 0. We will say initially how much is the count? Set count as 0. So update the count as increment or add column plus 1 value in the count variable. That is what we have done during the dry run. If let's say the element 5 was the answer, it was having less than equal to mid value. 1 was also the answer. So how many elements were there? Count plus 1, column plus 1 actually were the number of elements. And increment the row in this case. However, increment the row, that is row plus plus. However, if it is not the element, then all the column elements will also be not the answer. So decrement the column. We have to do this. And finally, what we have to do is we have to just return the count, whatever the number of elements smaller than the mid value will come out to be, smaller than or equal. We are going to write the code in Java programming language. So what we are doing is we are saying left initially will start from the top left corner, that is array of 0, 0. And since the array name in this example is matrix, let's just say matrix dot get 0 dot get 0, because we are given a list of lists. And whenever we are given a list of lists in Java, we have to use get syntax instead of square brackets. Similarly, the right pointer will also be matrix of get n minus 1 comma n minus 1. But before that, actually, let's get the n value by doing what? By saying matrix dot length. You can use matrix dot length function actually, or instead of length function, there is a size function to get the number of rows or number of columns. Now, once we know how many number of rows or number of columns are there, we will say the last top right corner, the bottom right corner actually will be n minus 1th row, n minus 1th column. Last row, last column. Now, once we know the range on the binary search, we will start the binary search by initializing some answer value. As anything, you can initialize with left, right. I am initializing with right. Apply the binary search till the point left is either equal to or smaller than right. As soon as left becomes more than right, binary search range is empty. Every time find out the mid by just simply doing left plus right by 2. However, if you want, you can just apply a different formula of mid, that is left plus right minus left by 2. That is also a valid formula. Find out the count by calling the function which we have made to get the count. So I'm just right now calling it, passing the matrix, and also passing the mid value. Let's also pass n actually, because again we have to anyways use it. So let's also pass n variable, that is the number of rows, number of columns. So there are two scenarios in the binary search during the try run. What we did, whether the count is less than k or more than equal to k. If it is less than k, it is not the answer. If it is more than equal to k, yes, it is the answer, potential answer, not the final one. So if count is less than k, since it is not the answer, only update left as mid plus 1. However, if it can be the answer, first update the answer, because we are slowly going towards the answer. We are closing the binary search. We are reducing the binary search range towards the answer itself. So update the answer variable as the current mid, but decrease the range by making right as mid minus 1. So this is the entire binary search logic. Finally, of course, we have to return the answer. But if I will run for now, obviously it will show me some errors that this function is not going to return anything. But let's see another compilation errors if there are any in the second function which we have written just now using the instruction manual. So as you can see, there is only one error, that kth smallest element, this find smaller elements, this function is not returning anything. So let's just directly implement the stepped case search. For that, what we have to do is we have to again set a row variable and a column variable, but this time starting from top right corner, row as 0, column as n minus 1, and also set the count which we need to find out as 0 initially. We will run the loop till the 2 pointers are within the matrix, that is till row is less than n as well as column is more than equal to 0, because column will go out of the matrix from the left side, from the left hand side, because column is becoming minus 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 minus. It will become minus 1 when it is out of the matrix. Row, since it is becoming plus plus, it will go out of the matrix when row is becoming n. So we are running the loop till row is less than n as well as column is greater than equal to 0. Every time check whether it is less than equal to mid or not. So if the matrix dot get row dot get column, is it less than equal to the mid value? If it is, do something, otherwise do something else. If it is, first of course, count will get incremented not by 1, but by the entire row elements till the current column, that is till the column plus 1 elements. And of course, we have to also discard the row because it is counted now by doing row plus plus. If you are not getting what we are doing here, just please watch the concept video. We have discussed completely that what we were doing in order to do row plus plus or column minus minus, why we were doing all of these stuffs. Anyways, now finally what we will do is we will just return the count, whatever the count we are getting, that will be of the smaller or equal elements. So let's see if our logic will work fine or not. We are able to complete the code. Sample test case is working. The 8th smallest element is 13 according to the sample input. If I will use the same test case and just change the value of k from 8 to 5, the test case which we have taken in the dry run, it should come out to be 11. The 11, I guess, was the answer. Let's see if 11 is the answer or not. Yes. Let's submit it. And actually, before submitting, let's just also confirm for corner cases. What will happen if I'm saying first smallest element? First smallest element should come out to be 1. That is the minimum value. Let's see if it is going to give me the minimum value or not. Yes, it is giving me. How about the ninth smallest element? It should give me the maximum value, which is 15 in this case. Let's see if it is going to give me 15 or not. If yes, then we will actually submit it and then check whether it is working on all the test cases or not. So I am reducing the screen size. If you want to read the entire code, you can give a read, you can try on yourself. Most probably it will get accepted for all the test cases. Let's see. It is taking some time, but as you can see, all the 22 test cases, including the corner ones, are also accepted. As we have already discussed, the time complexity will be n times log v. Space complexity, are we taking any extra space? We are not taking any extra space as such, because the step case search is just a searching algorithm without extra space, as well as the binary search on the answer also is not actually creating array. It is just a number line on which we are applying binary search. So constant space n times log v time, that is the most optimized solution which you can get for the kth smallest element in a sorted matrix. We will meet in a new video with a new problem. Till then, bye bye. Take care.